Well, thanks very much. Really sorry, it's terrible being late for your own talk, isn't it? My excuse is that I was supporting a colleague in a research grant interview with the Research Council, and they overran, so I had to run from next door. But anyway, sorry about that. Anyway, it's really great, really great to have this opportunity to give this talk. And this is work. Actually, I've been doing this for quite a long time. And some of it has seen the light of day, but some of what I'm going to show you today hasn't before. It was initiated actually with Ben Veitch, who was a PhD student in Manchester with David, quite a long time ago now actually. And Ben Veitch came to Cambridge on a Crichton visiting fellowship in about 2007, and we started some work together. And then since then I've been coming back to it from time to time. Part of it I did jointly with David Abrahams himself as well, although I'm not going to talk about that today. So anyway, let me move on. So this is all about aero engine noise. This is a schematic of a typical large turbofan engine that you might see on something like a Boeing 777. The noise is being produced in all sorts of places. There's, of course, noise being produced in the core of the engines. So in these sorts of very large bypass ratio engines, a lot of the air goes around the outside, and as you can see in the so-called bypass ducts, but quite a bit, but about 5% of the air goes through the core and is accelerated and burnt with the fuel. And then comes out the jet in the core at the back. And so noise, as I say, is being produced all over the place. But I think, particularly at takeoff, what is now thought is the most troublesome sources of noise are coming from the turbo machinery sources. And so in particular, what you can see, the very large blade row at the front is a fan, which is rotating. So that's a noisy process of itself. All right, oh yeah. So there we are, there's the fan, so that's noisy of itself, but that fan then produces significant disturbances, wakes, which then propagate downstream, and they then interact with this row here, the so-called outlet gouge vanes, the stators, which are stationary, and that's very noisy as well. Some of that noise will propagate back upstream. Much of it will go downstream. And so probably at this stage, it's the stuff that's going downstream that is the thing of most concern. And there's a whole frequency spectrum of noise. There's sort of so-called tones which are associated with this, the rotation rates of this blade row and rotating blade rows in the core, but there's also a broadband spectrum as well. Now, the question is how might one control this noise? And there's one particular technology which is very classical actually, which has continued to develop, and that's by the use of so-called acoustic linings. And this is what this is sort of meant to represent here. Now, acoustic linings are essentially honeycomb structures. So you have this honeycomb structure, you have a hard base layer, and then there's a top-facing sheet which has been laser drilled and so is perforated. And of course, the idea is that the honeycombs are designed to a bit like Helmholtz resonators in reverse, really, to attenuate particular frequencies of noise, and so therefore stop them ever getting outside the aero engine and getting to observers on the ground. So the classical place to put the linings is here, but what has started to be thought about more recently, or at least it was recent when we started this work, was actually lining this part here as well. So that's the sort of schematic. So here's a model problem that we tried to set out to do, and this is what Ben Veitch and I started on way back in 2008. And you can see it is a gross simplification geometrically, but there are some key features about this that I want to highlight. One is that we've got two coaxial cylinders, so that's sort of representing that. Okay. Going the wrong way. Sorry. Two coaxial cylinders. This one in this so-called half-cowl configuration, so the inner cylinder protrudes some finite distance downstream, just like in the bypass duct jet configuration. And another key thing about it is that I'm really keen to represent the fact that there were different flow speeds going on. So externally, there's a, if we think about ourselves in a sort of maybe in a wind tunnel, then there's an external flow speed, which might be, if we're at takeoff, then that might be about Mach 0.2, so relatively low. There's then a so-called bypass stream, where that's where most of the air has gone around the outside through the fan and the OGVs. So that's a bit faster, and then you've got the much faster jet. This is still subsonic though, I should say typically. And so the question was, if we have some incident field here, so this is noise that's been produced from the, let's say, from the fan OGV interaction, that noise propagates downstream through the bypass duct and then gets scattered by the exit, and what gets to the far field. There's something I've noted here which I've sort of glossed over in the maths that comes later. But there's a key thing, of course, which I think is a really important part of the physics, is that these shear layers, of course, are unstable. They've got Kelvin-Helmholtz instabilities, and that, I think, is, if you miss those out, then the actual acoustic scattering goes all wrong as well. So I'm not claiming that in a real engine that there are vortex sheets, but there are definitely shear layers, and we need to include those. Okay, so there's that. There is an alternative formulation. You see this, I think, on some military aircraft. This is a so-called buried nozzle problem, and you'll see the difference now is that the jet pipe is buried inside the inside the bypass duct. So the interesting thing about this is that the mathematics, the way the Wiener-Hopf technique winds out, is quite different in these two problems. So today I'm going to concentrate on this problem, but it turns out that this problem's a bit easier. Okay, and I'll try and highlight that a bit later. Now, just to say what's been done before, and therefore what I'm telling you today, which hasn't been talked about much before. So what Ben Veitch and I did originally was we took all of these walls to be hard. So there was a Neumann condition, zero normal velocity on all walls. Okay. And that was all fair enough. But what, as I just said when I started, I was really keen to do was to include the effect of these acoustic linings. And so what we've done, for definiteness, is in this later work, we've now put an acoustic lining on the outside of the jet pipe. Okay, so there's one wall which will have a so-called Robin boundary condition on it. I'll show you what that is in a minute, but all other walls will keep the Neumann condition. And I could have put the acoustic lining there, but just put it somewhere for definiteness. Right, so previous work, as I just mentioned, all walls were hard. This seems like yesterday, but of course it's a very long time ago. And then the more recent work on with the linings is what David and I have done more recently. And this sort of started to get to tackling some of the difficulties of putting this lining here, having the Robin condition. The work we did with David was just for this buried case, so I'm not going to mention that here. But it was a great piece of work, wasn't it, I thought. Right, so here's the governing equation. So it's really just Helmholtz equation, assuming everything's linear. This has got source flow convection in it here. So there are these three Mach numbers, M1, the jet Mach number, M2, the bypass number, Mach number, M3, the outer flow, exterior flow Mach number. It looks like I've got the sound speed on the wrong side of the equation. That's because of the normalization that's been done. This notation I inherited, I didn't choose it, but this is actually inverse sound speed squared. And it's important to include that because the jet is, even though it's subsonic, is very hot, and so there are significant variations in sound speed between the three layers. And then I mentioned, well, the boundary conditions, we've got zero normal velocity on all the walls which are hard. And then on that, that one wall, which is, so R equals A plus is the outer surface of the inner cylinder, X less than D is the semi-infinite inner cylinder. We've got this boundary condition here, and this is the sort of industry standard simplification of how to model this really complex honeycomb perforated lining structure. So you'll see what we've got here. So this is normal velocity, unsteady normal velocity here. This is the acoustic pressure here, and these two are related via this. And Z is the impedance, which is meant to represent this really complicated acoustic lining. So Z it's frequency dependent, although that won't matter because I'm treating a single frequency at a time. And Z is also a complex number, and it's so there's there's a real part of it which is related to the amount of energy that the liner absorbs from the outer flow. So, and that would be real positive here. So we've got that boundary condition there. We've got vortex sheets, shear layers, so we've got to do the proper continuity of particle displacement, and we've got to do continuity of pressure across the wakes. And obviously I'm going to have a radiating flow. And I've already mentioned the Kelvin-Helmholtz instabilities, which need to be included in there. So to proceed, what we're going to do, of course, we're going to take a Fourier transform in the axial direction, complex wave number alpha. Right, so there's a huge amount of mass and complexity and horrible algebra included here. But what the Wiener-Hopf problem comes down to in the end is this thing here. Now, when Ben Weitsch and I did the hard walls everywhere, it turned out that this was a 2x2 problem. Okay, but as soon as we get the wall lining, then it becomes 3x3, and you can sort of understand why that is, because this Robin boundary condition is telling you neither the pressure nor the normal velocity. It's just giving you a relationship between the two. So you've sort of added an extra degree of uncertainty. But this is the Wiener-Hopf equation. So there's this unknown vector here of the functions which are analytic in the upper half plane. So these are all to do with the way that the shear layers flap up and down as they, the sound comes through. There's unsteady flow flapping the shear layers. So we don't know what those are. That's on the outer shear layer. That one's on the inner shear layer. And this function here is something else, which is to do with essentially the difference between the pressure and the normal velocity. So this has got the impedance in it, even though the impedance doesn't matter downstream. So that's unknown. And then there's another one over here. So these are quantities which are analytic in the lower half of the complex alpha plane. And these are all to do with the unsteady pressure jumps on the two cylinders. So those are three things there. That's a normal velocity, actually. But anyway, that's all got mixed up. So this is stuff on the upstream boundaries, if you like, and this is stuff on the downstream boundaries. And of course, it's a mixed boundary value problem. And then this thing here, this F, is the forcing. So the forcing is provided by the sound that's incident from upstream that has come from your rotating fan or whatever. And that alpha inc minus is the wave number of the incident wave. Right, okay. Here's the matrix, and again, there's a huge amount of, it's one of these problems you wish you'd sort of never started, but then there's a sort of curious thing that you could never give it up. But let me just point out a few things about this Wiener-Hopf matrix, where I think a few structures which are really important. So the first thing to emphasize, I think, is these exponential factors here. That one e to the I alpha d, e to the minus I alpha d, there's another one there. So remember, d is this finite distance. So if you like, two cylinder exit planes, the bigger one and the smaller one, we're doing the case in which the smaller one, the inner one, protrudes. D is a positive number. And these exponential factors, I think you see these in all these sorts of problems where you've got this sort of finite separation between two scattering planes. There are some loads of functions over here as well, which are sort of wall-to-wall Bessel functions. Just point out there are a couple here. This sort of gives some confidence that sort of you know things are working out okay. So there's this function here, capital delta. So that capital delta equals naught is the dispersion relation in this region here. So that's an outer cylinder with an inner cylinder with a lined wall, and so delta equals naught of all the modes, gives you all the modes that can occur in that region. Region B, the interior jet pipe here, so this on Im prime derivative of the modified Bessel function, so you can see how that's cropping up, and that relates physically to the waves that are allowed to propagate in the jet pipe, which remember is hard inner walls, so that's quite straightforward. And then finally there's this function h, which crops up all over the place as well. H equals naught corresponds to the overlap region. So this is the overlap region. So in the overlap region, you've got one vortex sheet, you've got a lined wall, you've got and you've got a lined wall, and then what are the waves that can sort of propagate there. So you can sort of get the idea of how things are slowly being pieced together. And the whole point is that we need to do the Wiener-Hopf factorization of this matrix. And this is how I've done it. There are no partial indices here, actually. I don't think I can prove that I don't have any partial indices, but numerically it's never cropped up, so I'm pushing on. But anyway, what we need, of course, we need K minus and K plus to be analytic, invertible, and with algebraic behavior at infinity in their respective half planes. And if we do that factorization, and we go back to here and do the usual stuff about rearranging this equation, then what we end up with is this thing here, and everything looks all very nice and very straightforward. So you can see how I've taken off in very standard fashion the residue of the pole corresponding to the incident scattered wave. And of course the point is, I hope that everything on the left-hand side is now analytic in the upper half plane, everything on the right-hand side is analytic in the lower half plane, so we've got an entire function. What's the entire function? So at that point you've got to start thinking about the conditions at the edges of the jet pipe, and there's a little bit of messing about here, I must admit, but the rigid one, it turns, this is a full cutter condition in the lingo. The rigid one, the pressure jump goes like distance to the half from the edge. The lining one is a bit different, interestingly, but you can get all that. But putting all this junk together, you get that the entire function is zero. So the magic of Wiener-Hopf saves you. Right, so that was formally, that will look very nice, but there's now this great question of how do we actually do this? And this is the thing that occupied Ben and I for ages and ages. So if we just look at this equation, and we, in this case, equate elements in row I and column 1, then you get something like this after a bit of rearrangement, where I've had a function here. Remember, this delta and this h are really sort of crucial in the problem. I've been able to do a scalar factorization of that, and I've rearranged all this junk, and it looks as if I've solved it, because you'll notice almost everything on the left-hand side looks as if it's analytic in the lower half plane. The exponential, because d is positive, is exponentially small in the lower half plane, so that's right, and everything on the right-hand side looks good. But the key thing is this function h, which is again a great mess, I'm afraid. But the problem with h is that h is not a meromorphic function. Now, if it were meromorphic, and it just had zeros, then what you could do, obviously, would you be doing pole removal? But the trouble is that this thing has got a logarithmic branch cut, and you can't do that. So the step that we did, and this again inspired by David Abrahams, was instead of doing that, was to replace this exact function by a rational function, by a Pardee approximant, H0, which is meromorphic, and then once you've done that, you can then do pole removal on the approximate Wiener-Hopf problem. So there's got all these zeros, infinite number of zeros of the Pardee approximant in the lower half plane. That's all I'm interested in here. So you can then proceed. And sorry, this is a horrible mess, but I'm just sort of indicating really how, even though it looks messy, it is quite straightforward. So what's gone on here, you see, is that I've got all these zeros of H0, the Pardee approximant, in the lower half plane, and all I've done is simply subtract off the residue of all this stuff at those poles and add it back on the other side. So it really is the case now that everything on the left-hand side is analytic in the lower half plane, everything on the right-hand side is analytic in the upper half plane, and you can do your Wiener-Hopf again. And there's a lot more messing about to it than this, but I mean, this is the key step, I think. So just a word about the Pardee approximant, what that thing, that H that I'm working on boils down to is it's got this thing in it, this ratio. So I and K, of course, are what happen when what you get when you separate variables in Helmholtz equation in cylindrical geometry. I is the one that's regular at the origin. K is the one that's has got the logarithmic singular branch point, but is better behaved as infinity. So this is sort of associated with the radiation going to infinity. But the key thing is that it's not meromorphic. So it proved, this is experimentation, it proved better. So you really need to work hard to get the behavior at infinity right before you do the Pardee approximant. So that's what we did actually. So we didn't Pardee approximate this straight off. We took this sort of modified thing and did the Pardee approximant on that, because doing this actually fixed the correct behavior at infinity. And just to indicate how accurate that is, this is in percent relative error. So you can see 0.45, 0.045% relative error with quite a modest size of Pardee approximant actually. So it did work quite well. And I should say that the inversion contours are not simply the real axis. You've got to indent the inversion contours to take account of those Kelvin-Helmholtz instabilities in the shear layers that I mentioned. And I think this is what's causing this worse behavior here, but it's still minute. Anyway, pushing on, so that I've already shown you about the first column in that K minus K equals K plus. You've got to do the same thing for columns 2 and column 3. And the agony isn't over, because now it turns out to do those. You've got this 2x2 submatrix K twiddles, which you've then got to factorize as well. You can see here H0. So again, I've used that Pardee approximant to replace the exact H by the approximate H0. I'm not going to talk about the factorization of this, except there's another scalar. I don't quite understand why I've got to do another scalar factorization sort of as part of this. But what's sort of going on, you might well ask, with all these factorizations? Well, I think if you look at the parameters, the physical parameters that are appearing in these two matrices, so this matrix K, the 3x3 Wiener-Hopf matrix, is really associated with everything that's happening downstream of x equals d. So everything down here, the parameters don't depend on this stuff, but they do depend on all of that. If you looked at K twiddle in isolation, this 2x2 submatrix, then that doesn't know anything about what's downstream of x equals 0, that's a downstream of here, but it does know everything about up here. And so if you were solving somehow uncoupled problems, then these two matrices you'd do them separately. But of course these two flow regions, x bigger than 0, i.e. there, and x less than d, i.e. there, overlap, and that's why you've got to do this coupling and factorize K twiddles as part of the factorization of K. So that's my sort of very simple-minded justification of what's going on here. Okay, I'll give you some results just to prove I can do them. So I'm giving you far field acoustic pressure. This is all very standard stuff. So you do steepest descents to get a directivity. This is just a typical, this is a cylindrical decay. So, and you then have this. This is the directivity. Theta is the angle to the downstream direction. And after all of that, pages and pages of Wiener-Hopf stuff, the solution is sort of included in this one number, which you can see is a particular value of the transform of the vortex velocity evaluated at a yeah. It's the HR manager chasing me. Sorry, should turn that off. I'll evaluate this out at the saddle point. So anyway, so that's that. And there's a sort of question: what's the input power? Because remember, I've got this infinitely long jet pipe. So any sound that had propagated inside this infinitely long pipe would have been attenuated to zero by the time it got to the outlet. But of course that doesn't happen in practice. Your engine's only a finite length. So this has all been normalized. So the incident power is unity when it actually gets to the origin. Right, so here are some results. There are two different incident modes, and I've got sort of representative parameters here. Don't know to what extent you can see these, but what I'm doing is I'm varying the amount by which the inner pipe protrudes beyond the outer pipe. So there's no protrusion at all, so they're both in plane, and that is the biggest sound. It's all beamed in a particular direction, which is sort of chosen by the incident mode. And then, as you might expect, perhaps, as we protrude this, the inner jet pipe further downstream, it's got this acoustic lining in. That acoustic lining is reducing the noise that's being produced, so the sound goes down. And there's a result for an infinitely long inner pipe, which is a scale of Wiener-Hopf, and it's sort of tending to that quite rapidly. Here's something for varying the impedance, and that's the infinite impedance, which is a rigid wall. As you increase the softness of the lining, the sound goes down, which is hardly surprising. And this was, I'm coming up to the end of my time, so I might just sort of finish with this slide. So this is the so-called power level, and what this is you integrate the total acoustic power over all observer directions. So this is how much acoustic power is being radiated, and so I'm plotting the change in that when compared to the purely rigid case. So if you like, this is how much sound attenuation is your very expensive acoustic liner buying you, right? Along here, I've got log 10 of the hardness of the impedance, so the real part of the impedance along here. Here's the delta power level. Obviously, it all goes down, which is good news, but there are some things to see here. There's a sort of there's definitely an optimal value of the hardness of the impedance, the real part of Z, which produces the biggest change in power level, and this is for different values of the stack. Right, I'll bother with that. So here are my concluding remarks. I think it has felt like a big extension of what we've done already. It was certainly an awful lot of work, and there's these conclusions about the effect of the linings, and you could extend it to include linings on yet more walls, but somebody else had better do that because that's far too much for me. Anyway, thanks for listening, and sorry for going over.
Thank you very much. We have very short time, but please have some questions.
Thanks very much, Nigel. Lovely talk. So you commented on the Kelvin-Helmholtz instability. So is that affected by adding the liners?
No, but the liners do have their own instabilities as well, which weren't in the parameter range that we considered. But you would strictly, in a different regime, you would have to include those. But the Kelvin-Helmholtz was definitely just the shear that, yeah.
And another observation is you could have done your results for negative D as well as positive.
Yes, I do have those. Yeah, so for negative D, you don't have to do the Parde approximant because it turns out that for negative D, the equivalent of that H is a meromorphic function. So you just do, just in inverted commas, do the pole removal and that goes through. And the results do, the negative D as D tends to 0 agree with the positive D as D tends to 0, which is fortunate, yeah.
But do you get greater sound shielding by having that protruding inner one?
No, it doesn't make, the lining doesn't make much difference actually when it's inside, yeah.
Nigel, when you introduce your line, you mentioned that this is connected Helmholtz resonators.
Yes.
That would involve strong frequency dependency.
Yes.
But when you showed your plots, Z is a constant.
So this is all for single, everything I've shown you is single frequency.
Oh, okay.
At a single frequency, but you're absolutely right. And there's a big industry in trying to do experiments to measure the frequency dependence of the attenuation of the lining. Yeah, yeah.
I have a question. You showed us the accuracy of the approximation and showed that actually very good in only a few. Yes. But the question is, have you controlled actually what is the behavior of the factors after this approximation? If you try few close fuzzy approximations.
If the behaviour of the
behavior of the factor k plus and k minus depending on what type of.
yeah, no, that's right. So they're fixed to still have the right algebraic behaviour. Yeah, so that's definitely, yeah, you're right. No, that's really important. That's part of it, and that was part of getting the behaviour at infinity right. Yeah.
Thank you. Was there an upstream peak in directivity? If I
There was there was
on the left-hand side.
Yeah, there was.
Was
for that particular,
Okay.
yeah, there was for that particular mode, and
Much
that was
smaller.
sort of back scattering. But that was. I think that's the sort of, in the lingo, is a strongly cut-on mode. So it really just was going straight through essentially. But if you had higher order modes, then you're right. Then there's a lot more upstream. Yeah.
Okay, thank you very much to Nigel.